Hi everybody, welcome to our module on the basal ganglia. The basal ganglia are a collection of nuclei just above the brainstem beneath the cortex, and they all work together to coordinate complex motor movements. And the names of the 5 basal ganglia structures that you need to know are the substantia nigra, the subthalamic nucleus, the putamen, the caudate nucleus, and the globus pallidus. It's very important that you're able to find all these basal ganglia structures in cross-sections of the brain, either anatomical cross-sections or in radiology images. And you should practice doing this using your anatomy textbooks. Go through and make sure you can always find the basal ganglia components. But let's just do it here in this coronal section of the brain. So we'll start with the caudate nucleus right here, and it's always easy to find because it's just outside the lateral ventricles. These white things are the lateral ventricles, and there's a caudate nucleus on each side. Just below the caudate nucleuses are the thalamus, which is not part of the basal ganglia, but the basal ganglia greatly influences the thalamus activity. Over to the side here are 3 structures. The big one on the outside is called the putamen, and the 2 smaller ones in the middle are called the globus pallidus. And then down here at the bottom we have the subthalamic nucleus on top and the substantia nigra a little bit lower down. So make sure you understand where all those structures are in this image and in other cross sections of the brain. When we talk about the basal ganglia, you'll hear us talking about the striatum, and what do we mean by that? Well, the striatum is 2 structures together, the putamen and the caudate. And if you look down here in this cross section, you see the caudate nucleus up here next to the ventricle, and the putamen is down here, and they're divided by the internal capsule right here. And these 2 structures work together. They receive major inputs from the cortex, and we'll talk about what they do in a minute. You'll also sometimes hear people talk about the lentiform nucleus, and what do they mean by that? Well, if you look down here in this picture on the left side, you see the putamen and the globus pallidus together. These structures all together are often called the lentiform nucleus. The function of the basal ganglia is to modify voluntary movements. If you think about things you do with your hand, like throw a ball or play a guitar, this is a very complex movement. Some muscles have to be activated, others have to be deactivated. It's not a simple on-off of one muscle group, and the basal ganglia is what coordinates all that. It gets input from the cortex to tell it what the body wants to do, and then it provides feedback to the cortex to either stimulate motor activity or inhibit. Usually it does both to generate a complex movement. This combination is what helps us do complex maneuvers with our body. So to explain this in a little more detail, imagine that you want to do a complex maneuver like play a guitar chord. Your premotor cortex will decide to execute this movement, and it will activate the basal ganglia. The basal ganglia will then use something called the direct pathway to activate muscles that are helpful to playing that guitar chord. It will then also use something called the indirect pathway to inhibit muscles that are not helpful to that guitar chord that you want to play. And it will send the feedback to the primary motor cortex from both the direct pathway and the indirect, and this combination will generate the complex movement or action, and you will hopefully get the chord to sound right on your guitar. So to understand the direct and indirect pathways, we first have to understand how the elements of the basal ganglia interact. So let's talk about each element on the screen here. First we have the cortex, and it wants to stimulate the brainstem and spinal cord over here to do motor activity. In the middle of the screen we have the coordinator, sort of the general of this whole process, and that's the striatum. It can communicate with the substantia nigra over here on the right side of the screen, but it communicates with 2 sections of the substantia nigra separately. One's called the pars compacta, and one's called the pars reticulata. Down here at the bottom we have the globus pallidus, and there are also 2 separate components of that structure that are important for the basal ganglia. The first is the globus pallidus externus, and the second is the globus pallidus internus. Over here we have the subthalamic nucleus, which also plays a role, and then finally up here we have the thalamus. It's essential that you understand that the thalamus wants to stimulate the cortex. It wants to tell the cortex to send signals to the brainstem and spinal cord to create motor activity. The reason this doesn't happen constantly in your body is that the thalamus is held back. It is inhibited by 2 key structures, the globus pallidus internus and the pars reticulata. So when you are at rest, both the globus pallidus internus and the pars reticulata are pouring GABA onto the thalamus, and this is inhibiting the thalamus. It's called tonic inhibition of the thalamus. Because that is occurring, the thalamus can't do what it wants to do. It cannot activate the cortex, and therefore the cortex is not being stimulated to activate the brainstem and spinal cord. And that's why you get no motion at rest, because the thalamus is held back by the elements of the basal ganglia. When you want to create a movement, the direct and indirect pathways are going to modulate that inhibition of the thalamus to get the movement that you want. So now let's talk about how those elements of the basal ganglia work together to stimulate movement. And remember, when you're stimulating movement, that's the direct pathway. So the cortex decides that it wants to commit to a complex maneuver. It will dump glutamate onto the striatum, and glutamate is an activating neurotransmitter, so this will activate the striatum. The striatum will then dump GABA on two key structures. The first one is the pars reticulata of the substantia nigra, and the second one is the globus pallidus internus. And you may recall that these two structures are what inhibit the thalamus. Now, GABA is an inhibitory neurotransmitter, so when you dump an inhibitory neurotransmitter on these two structures, you decrease the activity of the globus pallidus internus and you decrease the activity of the pars reticulata. That means they stop holding back the thalamus and they free the thalamus to do what it wants to do, which is to activate the cortex, and then the cortex can activate the brainstem and spinal cord and create a movement. This is how the direct pathway works, and this is fairly easy to understand. Basically, you are just shutting down the pars reticulata and the globus pallidus so that the thalamus can be free. The only confusing part is there is a little side amplifier of this system. At the same time the cortex activates the striatum, it also activates the pars compacta of the substantia nigra. This will stimulate the striatum with dopamine through D1 receptors, and that just sort of amplifies the whole process. Some people call it a kickstarter or a modifier of the whole process, but it's not really the main thread. The main thing that's going on is you're holding back the globus pallidus internus and the pars reticulata so the thalamus can do what it wants to do. Now let's talk about how we inhibit movement through the basal ganglia, and this involves the indirect pathway. So once again, the cortex decides it wants to do a complex maneuver, and it signals the striatum. But this time the striatum is going to do something different. It's going to dump GABA onto a structure called the globus pallidus externus. Now normally the globus pallidus externus is holding back the subthalamic nucleus by signaling it with GABA, which is inhibitory. However, when the striatum dumps GABA on the GP externus, it shuts down the activity of the GP externus. Therefore, the subthalamic nucleus is free to do what it wants to do, which is to stimulate the globus pallidus internus. Therefore, the GP internus, which normally holds back the thalamus, now holds it back to an even greater degree, and the thalamus is even more inhibited than normal, and so it inhibits the cortex even more than normal, and you get decreased activity to the brainstem and spinal cord for movements that are unhelpful to a complex maneuver. Now, just like with the direct pathway, there's a little side part of this, a little kickstarter of the process. The cortex, in addition to stimulating the striatum, will stimulate the substantia nigra pars compacta, and it will inhibit the striatum through dopamine and D2 receptors. This is a little side part of this process that modifies the main thrust of the process, which is to inhibit the thalamus. So all that can be confusing, so let me summarize the key points. The direct pathway's goal is to create movement. It does this by having the striatum inhibit via GABA the globus pallidus internus and the substantia nigra pars reticulata. The GPI and the pars reticulata therefore stop inhibiting the thalamus, and then the thalamus is free to activate the cortex. And the modifier is the substantia nigra pars compacta, which modifies the striatum via dopamine and D1 receptors. So for the indirect pathway, the goal is to further inhibit movement beyond the basal state, and it starts by the striatum inhibiting the globus pallidus externus via GABA. The globus pallidus externus then stops inhibiting the subthalamic nucleus. This allows the subthalamic nucleus to stimulate the globus pallidus internus, which then further inhibits the thalamus beyond the basal state. Once again, the substantia nigra pars compacta is the modifier, but in this case it modifies the striatum via dopamine and D2 receptor. So I find it easier to remember the modifier role of the pars compacta separately from the main actions of the direct and indirect pathway. And if you want to do that, you can just remember that the substantia nigra pars compacta modifies the direct pathway via dopamine and D1 receptors. It modifies the indirect pathway via dopamine and D2 receptors. And the reason we care so much about this modifier process is because this is what is destroyed in Parkinson's disease. Parkinson's is a dopamine deficiency disease caused by loss of these dopamine pathways from the substantia nigra to the striatum. It's been heavily researched and studied, and we know a lot about it, and that's why it comes up so much on the board exams. So since the basal ganglia's job is to inhibit the thalamus, any damage to the basal ganglia will result in unwanted movement. The thalamus will be freed when you don't want it to be free. So all these movement disorders occur because there's damage to the basal ganglia. Parkinson's, Huntington's, hemiballism, Wilson's disease. When you lose the basal ganglia's inhibition of the thalamus, you get unwanted motion. So in this slide, I've noted the movement disorders in the portion of the basal ganglia that they affect. So in the middle of the screen, Huntington's affects the striatum. Down here on the left, hemibolism happens when you get damage to the subthalamic nucleus. That can happen from a lacunar stroke. Over on the right side of the screen, Parkinson's affects the substantia nigra. And then Wilson's disease can affect the globus pallidus and also the striatum. And that concludes our module on the basal ganglia.